Welcome to this first of two recorded lectures for the Part A lecture notebook for Module 6, the beginnings of machine learning. So this is a follow-up to the prologue lecture notebook that involved linear regression. And you're going to see, and we're going to discuss, some connections to what we were doing in this notebook and linear regression that was discussed in that previous notebook. In this particular notebook, we will be using, NumPy, Matplotlib for creating some plots of results and some widgets as well to make some of it interactive. We will also use pandas to read in some data from the web. So I provide some references here. I'm going to skip over this in this video, but there's plenty of stuff to read here in additional notebooks that you can get through these links and study, look around for extra resources if you're interested in pursuing more of this on your own after this course. So the learning objectives here are we want you to, well, first I should say this, an important note. Machine learning concepts will often appear harder than they are, and you shouldn't try to let this discourage you. If details elude you, just try to focus on the bigger picture about what we're trying to do and why we're doing something. The how we are actually doing it will come with time. By the end of the notebook, though, you should be able to explain what supervised learning means, implement and study the capabilities of two different types of artificial neurons as classifiers on various types of labeled data, explain the role of both training and hyperparameters in building classifiers, and then understand the importance of linear or almost linear separability on the performance of classifiers. So our first video will just cover this part A1, our first classifier, the perceptron, and there's just one activity in there. The second video will discuss the add-a-line. It will probably be a bit shorter than this video. This is an adaptive linear neuron. It's an improvement, I would say, over the perceptron, and you have just one activity there as well. And then there's a summary activity. I have done actually most of the coding for you. These activities are actually about just manipulating a lot of the code I gave you and just explaining the results and experimenting to see how changes you make to data sets can impact the quality of the algorithms for training these artificial neurons as classifiers on. So there's some additional useful resources that I provide links here that you might want to read. I highly recommend you do your own investigation. I'm going to focus more on high-level concepts. I will skip over some of the more in-depth mathematical details in this lecture notebook because I have written them out in detail and I've made illustrations of these in this notebook for you to read. And I don't really have anything to add other than what I wrote in this notebook. So you need to just kind of go through it at your own pace. In some parts you might have to read a few times. None of the mathematics is that particularly difficult, but it's just seeing how the pieces fit together that might just take time to help understand. But as far as the big picture on the concept of the perceptron, which is our first classifiers, the perceptron was developed more than 50 years ago, and it's based on a neuron model for a biological neuron. When you hear of neural networks or deep learning, what you're basically hearing about is something that's connecting many things that are like perceptrons or add-a-lines, for instance, just some type of neuron model together. So the more of these that you piece together, the more you're hearing about a neural network or deep learning, which means you have some layers of these neurons. Perceptrons are really a good place to start our initial meandering into the field of machine learning. There's some clear connections to linear regression, although there are differences that we will also emphasize. And let's just go ahead and talk about what a perceptron is. It is an algorithm for supervised learning of binary classifiers. So what is a binary classifier? Now, a binary classifier is a function which can decide whether or not an input represented by a vector of numbers describing the number of features, predictor variables, you could say, for a certain data, belong to some specific class. It is a type of linear classifier, and that's the part that makes it connected to linear regression, at least at some level. And that means that it's a classification algorithm that makes its predictions based on a linear predictor function that combines a set of weights with the feature vector. What does supervised learning mean? Well, simply put, it means we learn the function that maps the inputs to the outputs based on training data containing example input-output pairs. In linear regression, we have the data, the feature data, in the previous lecture notebook, there was the TV and radio and newspaper ad sales. And then it was how many of the actual object did you sell, as a result of your advertising dollars in these various media. So the output was continuous, the amount of sales, whereas the input functions had, these various features, 3 features. And we would have then like 3 weights associated with each of the features if we were doing a linear regressor, and then a bias that would describe how much you would sell of the object if you did no advertising. So those same types of things will show up here in terms of a weights vector and a bias for all the different features, except our output will be 1 or -1. So instead of saying, well, I'm trying to estimate how much I will sell of a particular item based on how much money I spend on advertising in various media, newspaper, TV, and radio, as an example, you might just ask, does this type of spending lead to an increase in sales or a decrease in sales? Sales. So that would be like this 1 or -1. Maybe the positive is you increase the sales, then it's 1, or -1, it's decrease. You're just trying to make a decision based on what the possible inputs are. So that's the kind of one of the differences is that output. It's like we have that line, which is like this part here, but when we feed that output of the line into a function to then turn it into a decision, a 1 or a -1. So mathematically, if you have x as an m-dimensional feature, and it could be, for instance, 1, 2, 3, 4, 1,000, it could be really any integer you want, a large positive integer. But, in the data that we looked at in the previous lecture was 3, because we had TV, newspaper, and radio advertising spending. Those were the features in the data. So we would then we want to figure out the weights, the W, which is an m-dimensional vector of weights, and B is the bias. This is a dot product that comes from linear algebra. We would use the numpy dot, or we've imported numpy as np, so it would be np dot. And we've seen that in module 2. When we take the dot product of the weights vector with x, we're just taking a summation. That's what that capital sigma means, from I equals 1 to m of wi times xi. And this is just a compact way of writing w1 times x1 plus w2 times x2, and then just keep adding all of them up, all the way up to w sub m times x sub m, where that would be the linear combination of the features, and then you add the bias term to it. So that's all we're trying to figure out, is those weights and that bias, to make sure that we're making the right type of decisions based on the type of features that we're feeding in, that we're classifying the outputs correctly. So the actual perceptron is then just making binary decisions whether or not the data that possess m identifying features, predictor type of variables, values, should belong to one set or its complement, represented by the outputs 1 and -1 respectively. So this is an abstraction of what a neuron looks like. And you have all these input signals, and there's myelin and all, cells, all sorts of stuff, and you get these output signals. Through mathematics and some imagination, you can build a perceptron model, which has the input signals, which are all the features, all the things that you're trying to base your outputs on. And notice there's usually, in a lot of literature, when you look at things, they'll call that bias term just the first weight, but they'll index it by 0, W0. I like to make it explicit as B, because it's not a feature data that you really get from the data set. It's its own entity. So I usually just treat the bias term separately, like W.x plus B, but in some places where you might read about this, you might just see W.x, and if you have M features, then X is M plus 1 in length, and this is an m plus 1 length vector, that W, and it's just that W naught is the first component you're indexing from 0 in that case, and the 0th component of X is always a fixed 1. It doesn't change with the data. The actual features of the data don't start until the second component indexed by 1. I think that's a more confusing way to present it, but I do want you to be aware of it. So for the sake of clarity and emphasizing the different role that bias has, and the formulas involved with learning that bias are different, I just explicitly write it out, like W.x plus B. But this, what we would do in linear regression, is this would be this line that we were trying to learn. And if you had a continuous output, right here at this point, you would have the output of what the line is, and you'd have all your data, and we would use those the errors, the residuals that we talked about in the previous lecture. You'd square the differences to the actual data, sum them up, and you'd get the sum square error. And we would use that and minimize it in order to figure out the optimal weights and bias term. What happens here is you feed the output of this line into this activation function that's -1 if what you get from this is a negative value, and it's positive 1 if what you get from this net input from the evaluation of this line gives you a positive value. And then you look at data that's already labeled with a 1 or negative 1 respectively, figure out any misclassification errors you have, and then you use that to try to update these weights in bias term until you get to a more optimal state that has minimized the number of misclassification errors. So that's a difference to the linear regression, is that linear regression is really starting here based on continuous data, not based on the idea of classifying what the outputs of that data are. So there's it might seem subtle, but it's a very important difference because it changes how we actually seek to minimize these errors and where the errors come from. So I also describe again this idea about the bias and what you'd see in other source material in the n+1 dimensional vector. So I already discussed this, so I'll skip over it. And I've already kind of compared it to a line of best fit, but I would recommend, again, you should read this through to yourself because I did take time to try to write this out very carefully for you so that it made sense if you read it. It might take a couple times to read it to make sure it all works. Now, when should you be able to actually get a perceptron to work? Well, a requirement, and it is a hard requirement, is that the data is linearly separable. So the idea that linearity plays some role is certainly not surprising, given that the analogy we've used so far is involved a line of best fit. But what exactly does linearly separable mean? It means that we can construct a line if we're in a two-dimensional feature space, the input space is two-dimensional, a plane for a three-dimensional input space, or hyperplanes for four higher dimensional spaces, that separates the feature space, the input data space, into two parts associated with the output classes. As an example, this is very abstract. I have an X1 and X2, so those would be two features. Maybe this is the radio spending, and this is the TV advertising spending from the previous lecture. And maybe the red dots are corresponding to classes saying if you have this mix of radio spending and TV spending, you're very happy with the resulting sales of the widgets that you're creating based on those types of advertising spending ratios. But if you spend maybe more on radio and not enough on TV, maybe you end up being quite disappointed with the resulting sales of the product. And so if you classify that, and so then the red is the happy and the blue is the, let's say, sad or disappointed with the sales, then what we're trying to figure out is a line such that when you make it equal to 0, that line goes between the two data sets, and then wherever you evaluate an x1 and x2, that leads to a w1 times x1 plus w2 times x2 plus the bias term. Whenever that turns out to be positive, you would like to then classify this to be 1, indicating you were happy. So that would be on this side of the line. And over here, w1 times x1 plus w2 times x2, right? The w dot x is just a shorthand for that, plus the bias term is negative. And that means our function output's -1, which means, if you were thinking of spending radio advertising dollars over here, or like on this part of the axis, but your TV advertising was down here so that it put you over in this region, then you would say, you know what, you're probably going to be disappointed with the sales. And the perceptron would lead you to that conclusion. That would be how you could use a data-guided decision. But you'd have to train it based on data you already had that had been classified. So there's some additional background material and illustrative examples you can read that I've linked to here. And again, I encourage you to take 15-20 minutes and just click through and start looking at this. But what I haven't discussed yet is how do you actually figure out these weights and bias terms? So there's a training algorithm that's necessary. Now, there's a lot of mathematics and notation here, and I've written out in bullet points, and I've been very careful in writing out what's going on. There's really just a couple of steps. It's a very iterative scheme. The main idea at a conceptual level, and you should read through this carefully. I have nothing really to add, and it would take a while to read through it. So I'm just going to kind of jump to this picture to say, look, what you could say is at the ith step of figuring out what the weights and bias terms maybe should be, you have some guess. You have your ith best guess and your ith best guess at B, at the weights and the bias terms. I'm assuming it's like a 1D feature space in this case. So imagine that you just have some data and you've been going through and iterating and trying to improve your estimates about what is the optimal weight and the optimal bias that leads to no misclassification. But let's say at this iterate, after you've passed through the data, the first I-1 data points, you look at the ith data point and you say, at that data point, when I evaluate this function, which is my activation function, it predicts a value of -1. But the actual data is 1. So I misclassified what that data is. Now I need to shift this function to the left. Or maybe I predict the value to be 1 at that data point, but at that data point, it's actually equal to -1. The class is -1. That's a misclassification error, and I need to move this function I basically need to shift that function to the right. In understanding how we shift functions, I describe all of this mathematically in terms of shifting the input by a negative or positive value leads to the actual updating steps. So again, I'm kind of skipping over this to focus more on the concepts, but you should read through it carefully. So the idea is like this. If I have n data points and I let my W superscript I-1 and B superscript I-1 denote the weights and bias terms used based on the, training it for the first I-1 data points, I get to the ith output data and I look at yi. Now, if there's no misclassification, right, so yi minus f evaluated by what I think the weights were based on the I-1th data point, and I have a bit of an error there, so I will go ahead and fix that. You can see me fix it here. That is clearly needs to be an I-1. Glad I caught that. Okay, there we go. So, and yeah, it's here as well. I'll fix those places for you. So that should be a B I-1, and that should be an I-1. I'll fix those typos. If there's no misclassification error, then there's not going to be any updating. So if I just happen to predict what the actual data is correctly, I don't want to shift the weights or bias terms. I have no reason to. But if there is a misclassification error, then I need to shift the weight from what I think at this current state, given by this I-1 superscript, to a new state based on this ith data. And the way I do that is I use that misclassification error, which is going to be signed. It's going to be positive or negative based on this relationship. I either predicted a -1 when it should have been 1, so 1 minus -1 is 2, or I predicted a 1 when it should have been a -1. And then you're using yi minus this, so that would be a -1 minus 1, -2. So the sign of this is going to determine how I shift the weight values, and I shifted an incremental amount by this learning rate R, so it scales this value, this misclassification error, and the sign of it, and I'm also multiplying it by the feature, because maybe the feature values are negative or positive as well, and I want to make sure to shift the weight value the right way so that the function is shifted towards reducing that misclassification error. The same thing happens with the bias, but you notice I'm not multiplying it by the feature vector here, and why am I not doing that? Well, quite simply, the bias term feature is 1. So it's a different formula. But I don't want to say more than that. These are the formulas. You do need to kind of read through and take time to do it. And then you just need to loop. The idea is that you loop through this over and over again. And every time you loop through all n data points, that's considered an epoch. And you might need to loop through them multiple times in order to get things to converge. So the idea of epochs and learning rates, like what are these things? They are called hyperparameters. They are things you need to kind of tune to make the algorithm work well for a given data set. And their values, what the optimal values for them are, really depends on the problem and on the data set you have. And that might not seem very satisfying because you have to kind of figure out, well, how should I select these things? Well, there's methods to try that are kind of ad hoc or systematic, but it's usually not apparent ahead of time what the optimal values are. And that's true in a lot of machine learning algorithms. You often have to make some sort of decisions on how you need to change values of hyperparameters in order to get the algorithm to work even reasonably well. There's some uncertainty in that, and that's true across many machine learning algorithms and pipelines of machine learning processes. But let's go ahead and visualize this to start trying to make more sense of this. These two code cells here are all you need to have in order to basically get a perceptron. So I have the activation function, which gets an x and a current w and b value for the weights and bias terms. I use the np.dot function to compute the x1 times w1, x2 times w2, and so on. All those values, I add the bias to it, and I'm using np.where to say, well, where is that greater than 0? And then wherever it's greater than 0, assign a 1. Wherever it's then less than or equal to 0, assign a -1, which is a very slick way of using the np.where function. So you should look at that. You might want to look up the official documentation for np.where to see how I basically get this activation function written as one line of code. And I just put it in the return. So I'll go ahead and run that there. So that's the activation function. And then the algorithm for learning the weights, it's very simple. It's this entire code cell. So you need to pass it your features, the X, all the inputs of all your data. It has a shape that is based on the features are in the columns. In the rows, so that's why I'm having the 0 here based on the shape, because the shape returns a tuple that says what the number of rows versus the number of columns are. And I want the number of rows to say, how many data points do I have? This is the N that is here. I'm just using lowercase in the code instead of capital. But you could switch it to capital if you wanted. And then I'm looping through the data. I look at the ith data point, yi. I know this is the training data where I'm going to learn these weights. So I know what yi is. It's supposed to be correct. It's a 1 or a -1. And then I'm subtracting from it this activation function, which then just evaluates this and then returns either a 1 or -1. And it's doing it on just each individual data. I'm looping through each individual datum that I have for the given W and B values. And now if there's no misclassification error, this error is 0, in which case that is 0 and that is 0. And if you look at what you're adding to the W and B values as a correction, so coming back up here, right, I want to move from this state to this new one. I want W equals W plus this value, or B equals B plus R, times this. And that's just that misclassification rate. That's all there is to it. There's your R times error times xi, and the B time is R times error, and it's plus equals again. And this just, there's no feature associated with the bias. I loop through all the data, and then I might choose to loop through all the data multiple times in order to get convergence. So that's it. As soon as you have these two code cells run, that's all there really is to it to build the functionality needed to talk about an artificial neuron that's called a perceptron, the perceptron neuron. Now, this code cell is doing nothing other than creating data that's linearly separable, but it's 1D data, which all that means is that where the data is -1 or where the data is 1 exist in intervals that do not overlap. The way they do not overlap is I associate a gap. So this gap value should always be kind of small. I have it at 0.2 here because I'm just creating data in the interval 0 to 1. And so in that case, I'm saying the first interval, if x is less than 0.1, where that 0.1 is 0.4, so you can change this value, then I'm going to create random data. You notice I have this random uniform data. I'm just generating it between 0 and 1, but then I start grouping it into these two separate intervals. If it's between 0 to 0.4, the value is going to end up being -1. If the data ends up being above 0.4 plus whatever this gap value is, and I defaulted it to 0.2, so initially it will be 0.6 to 1, then I'll make the data being 1. You should comment through the rest of the code to try to understand what these individual lines are doing, but it's just a way for me to generate a training data set. So now that I have that run, I can then call it. Notice I return a tuple, x data and y data. I just create the training data. I'm not passing any arguments because I have them defaulted. So this will generate 100 and I have the gap at 0.2. You can go ahead and change that, but I wouldn't necessarily change it right here in the activity I have you do. That's a good place to change it. So let me go ahead and run that. And now all of this will look kind of like what we saw in Module 4, where we have these kind of complicated looking functions that are just doing lots of visualizations. You should annotate, comment these lines of the code just to make sure you understand what each piece is doing, but it's just meant for visualization purposes. And then I have a widget, again, much like what we saw in Module 4, to explain everything. So what I'm feeding it are the X and Y data that I've generated. This is the training data that I've created here. And then I'm giving it the weights and bias terms as the initial guesses. And I'm initializing them at -5 and 1, but you can play with them between -10 and 10. And they're purposefully chosen to be bad initially. There's the learning rate, which you can also play with, in a number of epochs. So we're going to go ahead and do this, run that. And we can see with our initial guess, right, look at our data between 0 to 0.4. Here's the value of -1. Look at this random collection of data that's there. And it's all labeled as -1, the way that I wrote the create training data. That's what it's supposed to do. And between 0.6 and 1, using the default values, those values get 1. Now, in the blue dotted line, that's the initial perceptron. If I have a weight of -5 and a bias term of 1, and I just say, okay, W times X plus the bias term, what does the perceptron think should happen? Well, it thinks the data over here should be 1, and then it drops down to -1, and it thinks it's -1 forever after that. So you see it completely misclassifies all this data right here. This set of data it does correctly classify, but then all of this data is incorrectly classified because the values are 1 and then it's -1. Yet with one epoch through all that data, so by going through and incrementally changing all the data with a learning rate of 0.5, and yours might change a little bit because I'm not setting a random seed, so the data can be a little variable when you go to run it. But with what I have with this particular data, in one epoch, it managed to get exactly a weight and a bias term that lead to no misclassification. The learned weights and bias leads to this learned perceptron, right? The learned perceptron that exactly correctly classifies all the data because it's linearly separable. There's a nice gap between where the data is 1 and -1. There's no overlap, and it's just two separate intervals. That's what you need in 1D to have linearly separable data. That's what it means in a 1D feature space. So you can play with this rate, like I can make it, the smallest you can make it that I set them in was 0.01. Notice at 0.01, you shift the perceptron a little bit with one epoch. So it's trained through 100 data points. It's gone through all 100 data points, but it did it just once. And this small learning rate is making it so it just changes a little bit. So, okay, it changed a little bit, 0.01, and there's still a good amount of misclassification error. And you look at the weights and the bias, they are not -5 and 1. They've been updated by a pass through all 100 data points. If I say pass through all 100 data points again, so I go to 2, you notice the weights and bias terms shift, and the perceptron has shifted yet again. If I shift it again, I go through all the data again for 3 epochs, 4 epochs, 5 epochs, 6 epochs, 7. You see it's kind of slowly iterating because I have a small learning rate. It's taking a while until, boom, in this case, the 10th epoch. Now again, this might be a little different for you because I'm not setting the random seed here. And so you might want to start setting random seeds for reproducibility. But I'm not setting a random seed for the code. But now look, the weight is 0.04 and -0.02 for the bias. And that perceptron looks great. It's exactly classifying all the data correctly, which means if I gave it a new value of the feature for which I wanted to make a prediction, I would have better confidence that it would predict the class of what the output is 1 or -1 reliably because it's doing it right now for all the data. But those weights and bias terms are not what we saw before. 0.04 for W and -0.02, that's what we got by going through all 100 data points 10 different times with a learning rate of 0.01. But if our learning rate was 0.5, going back to the original, it was 1.79 and -1. And also look, that we got that with one epoch. As soon as it converges, so this happens at one epoch. If I go to 2, 3, 4, 5, so I'm treating through all the data, there's no updates to this. Why is that? Well, remember, there's no misclassification errors now. And if this error is 0 at every iteration, well, then that value is 0 and that value is 0. And so these incremental updates to the weights and bias terms aren't changing. You might ask yourself, why don't you just choose as large a learning rate as possible? So you could go to, in this case, I think 1 is the largest value. And I could, in this case, it converged, very quickly at one epoch. But if you choose a learning rate too large, right now I kind of limited it between 0.0 and 1. But you could change the number of data and the size of the gap. And if your learning rate's too large, it can be just as problematic if the learning rate is too small. And it's like finding that sweet spot so that you get the right level of convergence is tricky. With a learning rate of 0.1, for instance, right? You look at this, it's like the first iteration is quite bad, actually. And then the second one is right on. So that worked really well. It didn't do it in one iteration, but that worked pretty well. And again, the weights and bias terms are different because there's not a unique value. As soon as you get a weights and bias that works and there's no misclassification error, it's going to stop updating them. And there's potentially an infinite number of weights and bias terms that produce a perceptron for which there's no misclassification error given a fixed set of training data. That's a good thing to understand. This example is just a 2D example. So all I'm doing is creating data in boxes where the boxes don't overlap in 2D. So again, you should read through these and kind of understand. I have some code comments in here. This is just for creating training data. That's all it is. And I have defaulted 100 training points, but you could change that. And you could also change kind of aspects of these arrays here to change the positions of the boxes. I wouldn't do that here. I would create your own where maybe you copy and paste this and then call it like my create, where you can experiment. Just like here, I would, really encourage you to create like a, my create if you want to make any edits. For instance, like maybe you want 0.1 to also be a parameter that you feed into this. That's something that you might want to do. I mean, there's lots of things that you might want to play with as you think about this. I just try to make it somewhat simple initially. I'm just going to go ahead and run that. I'm going to create that 2D training data. And then this is all plotting. Again, it's just a bunch of plotting commands to do some annotated plots, make things look nice. And I'm creating 2 side-by-side plots. So again, I'm passing the training data, which is now 2D, because that X data and Y data, I just overwrote it with this create 2D training data. Previously, it was the create 1D training data, but it's just overwritten now. And I'm going to feed the X data and Y data into this. I now have 2 features because it's a 2D feature space. So I have a W1 and W2 for the weights that you initially can set, and a bias term. And then, of course, that you also have to initially initially guess and then try to learn from the data, and then a number of epochs in the learning rate. Let's go ahead and look at this. So here's the first, these 2 boxes. So here's one long, big, tall, skinny box that contains the data that has blue. So that's where the value is -1. And then I have this data where it's 1 in this other box. I'm just sampling randomly within a box. And you can clearly see it's linearly separable. And I chose an initial weights and bias that gives you a line here, but you see there's lots of misclassification. I choose the kind of salmon colored background, slightly pink background. That should be where the blue data lives, and the blue background should be where the red data lives. I did that for the contrast of the colors. And so you're looking for all the red data to be in a blue region for that reason, for the contrast so that it looks. And you're looking for a line to divide it. And you see at 1 iteration with a learning rate of 0.1, it's done a reasonable job. Like, it's done better perhaps than this. Like, it's gotten better. It's gotten closer to there's a vertical line that separates these 2 boxes. So that looks better, but there's still misclassification error. There's still blue data over here, and now there's actually some red data on this side. And again, yours might vary a little bit because I'm not setting random seeds. But if I go to 2 iterations, that almost did it. There's just this one misclassification error. It needs to be adjusted just slightly. So it will adjust at the 3rd iteration, and it looks like there's no misclassification. You'll notice these lines look a little choppy, and that's a resolution issue with how many points I'm choosing to plot to create the colored backgrounds and subsequently this dividing line. You could make it sharper with more points, but then it takes longer to make the graph. If I go to 4, you see, yep, that got it. Like that, there's no updates. 4 or 5, like it's got the data. It's fixed. It nailed it at 3? In this case, 3 epochs. And so you can go through, generate the data randomly again and again. If you set a random seed, remove the random seed and run it, and you can see how it performs with different sets. So now this leads us to the only activity for this part of the lecture notebook before we get to the add-a-line part, which will be covered in another video. The whole purpose of this activity is simply to build your intuition about the performance of the training algorithm for the perceptron. Now, I've certainly already made mention of ideas relating to performance, but it doesn't start to sink in until you do it for yourself. So for each question, or really for each part of this problem, I'm going to rewrite that for each part. For each part, you should try the code on different sets of training data with different size gaps in the classes to make sure that your statement comments are actually correct. Now, you could simply you don't have to copy and paste this code unless you want to make changes to it. What you need to do is you create a data set like X data 1, Y data 1, and maybe then you actually want to say gap equals 0.01 to make a really small gap. 0.1 is kind of a moderate gap. 0.3 would be a larger gap than what we had. And maybe you also want to look at what if the number of training data was 1,000. Now, I'm not saying do this here. What I'm saying, and maybe I'll just go ahead and show you, is you just can copy and paste that down into here, and you could create like an X data 1. Move my cursor out of the way. Y data 1, and create it. Maybe you want to create with 100 and gap equals 0.01. And then maybe you want it to be like 0.1 and let's say 0.3. And then you want this to be, let's say, 2 and 3 respectively. Like that might be something that you want to do maybe actually do it correctly. There we go. So now you have these different data sets, and there are 100. And then maybe you want to see it if you had different numbers of training data. Maybe you wanted to, then you run this, and then you can, copy and paste like these. In this case, you'd want to, that's 1D data. So you'd want to copy and paste like this chunk of code, and you would just be feeding it the X data 1, X data 2, X data 3, and so on with the Y data 1, 2, and 3 respectively, and look at the results and just try to understand what's going on as you change the learning rate or number of epochs for these different numbers of for these different training data, and then also look at it with less or more numbers of training data. Do that with another cell and another cell, and you're just going to run the code with different numbers of training data with different size gaps, and you're going to look at the sensitivity of the optimal weights and bias terms that are learned based on either fixing the initial guesses, so you might fix the data and then comment on the sensitivity as you adjust the learning rate, or fix a learning rate, comment on the sensitivity of the optimal weights, and this just keep doing it for different training sets. And then you might look at fixing initial guesses that are really not optimal, that are quite bad, and look at how many epochs it's necessary to get everything. You can just do it with the 1D training data. That's fine. That's where I've explicitly defined a gap. If you want to also do it with the 2D training data, then you should look at how you need to adjust these arrays in order to make them either farther apart or closer together in terms of this array of data. Maybe you want to move this box closer to this one where the data is, or make it move it farther away or somewhere else in space. You're going to have to figure that one out. You don't have to do that. It's just a recommended thing to do. You have to make sure that they're still separated though. So I'm going to go ahead and delete this because I'll give it to you clean. There we go. Now I do want to point out the unreality of linear separability exposed by realistic data. So I'm not going to read all of this to you, but it's something that you should really look through, because what I'm showing you is kind of something cool, is how I build kind of a little bit of a web crawler. Is I'm showing some stuff involving advanced team statistics. I'll just go ahead and run through the data real quick and show you what's going on. But what I end up doing is I create like a URL. So there's some nifty tricks here. Like I have a string variable that is most of what the URL is. And then I'm iterating through the years, which are numbers. I'm casting them as strings. So then I'm concatenating it to a string. And then I'm scraping the data from that URL. And then I'm taking the particular data frame I want from the list of data frames, and then I'm grabbing the certain statistics I want in terms of offensive and defensive efficiencies from these data frames. So I'm using all sorts of stuff that you saw in Module 5. I'm just kind of putting it together, and then I'm getting multiple years of data from advanced efficiency statistics, and I'm showing this is what, based on offensive efficiency and defensive efficiency over the last 15 or 20 years or so, whether or not a team ended up in the playoffs or missed the playoffs. And so in red, it's made the playoffs. In blue, it's not made the playoffs. And you look, this is not separable data. It's not at all, because the red and the blue data are kind of all intermingled. There's no way to draw a line that separates the two of these. And this just illustrates, like, you can't train a perceptron on this. And I show, for instance, here, like all I did was take that data, like what I asked in the activity. Basically, you copy and paste the cell, and all I'm doing is feeding the data, which are the basketball features, which are the offensive and defensive efficiencies, and the playoffs, whether the team made the playoffs or not. And I'm just showing, I chose an initial guess that looked kind of good. And so there's some misclassification error for sure, and there's always going to be. But if I look at taking the number of epochs from 1 to 2 to 3, now, okay, at 3, it looks pretty reasonable, but there's a lot of misclassification error. It doesn't look as good as the initial one. And then at 4, it's worse. And at 5 epochs, at 6, it just jumps around. Even when it looks like it gives a reasonable one, like after 8 epochs, I go to 9 epochs, it jumps around. It will never converge. You will never find weights and bias terms where you go, oh, that's it for the perceptron. You just cannot train a perceptron on this data because it is not linearly separable. And this is, what I kind of get at in this closing remarks. Again, you should kind of read through. I'm hinting at other things that are, learned when you study more about machine learning. But what the adeline neuron does is help us figure out a way to work around this, because we still want to be able to make a decision about whether or not a team is likely to make the playoffs or not likely to make the playoffs based on certain efficiency statistics that they have. Excuse me. And you just can't do it with the perceptron, but you could do it with the add-a-line. What the add-a-line basically does is it allows you to live with a certain amount of misclassification error because you're assuming you don't have linearly separable data. And it is even more related to linear regression. But I'm just going to go ahead and end this video at that point. Thanks for listening, and I'll talk to you in the next one.